This section is going to deal with the dimensions of physics and how they're measured and the units and converting units. First thing we want to look at is how do these units help us make sense of the universe? If we did not have units, then we would not be able to convey to someone else exactly what we were talking about. And so units help us have a way to communicate the measurement that we're trying to get across. So we have an international system for units. This was established in France in 1799, and it's really related to multiples of 10. The abbreviation for it is SI, and what you'll find is there is one unit per each dimension. So there's one standard unit for every dimension that we're going to deal with. So the first meaning of the word dimensions is just the number of spatial coordinates required to describe an object. So if you look at this example here, a point in space does not have a dimension, but a line is one dimensional. A plane or the coordinate plane that we're used to, that's two dimensions. And then when you look at objects that have depth, that is three dimensions, three-dimensional objects like a sphere. The second meaning then is a measurable physical quantity. All right, so then we're going to get to the actual measurable quantities. So each dimension is going to be described by a specific unit, and there are three principal dimensions: space, time, and mass. So the three principal dimensions here are space, time, and mass. So let's talk about space. Does require a unit of length. That standardized unit that we use internationally is the meter. Originally defined by a physical object, the present definition of meter is related to the speed of light. So the way we get that measurement is based on the speed of light. The second one is time. Obviously, time is a little more difficult to define because time can sometimes seem relative, but there is a standardized unit here for time, and that is the second. Originally, time was defined to mean a solar day. The present definition of a second is related to the oscillating cesium 133 atoms. This oscillating clock is accurate within 3 microseconds per year. So when they define this, this is a very accurate definition of a second. The third one is mass. And so the amount of matter that is contained in an object is the mass. It is different than weight. Weight actually has direction and mass does not. And so the standard unit for mass is kilogram. Mass is also related to an object's tendency to resist change in motion, which we'll talk about when we start talking about Newton's laws. Um, and so it was originally defined in relation to the mass of a volume of pure water. But as we moved to the present definition of kilogram, it's based on a constant called the Planck constant, which is a physics constant that will later be talked about as well. There are some other fundamental standard units that we will talk about as we get to more in-depth studies. Those are the Kelvin, the mole, the ampere, and the candela. And so these will be introduced as we get into other chapters regarding temperature and light. So if you look at the basic fundamental standard units here, you have length, time, mass, you have temperature, amount of substance, electric current, and luminosity. And so you'll see the symbols there for them as we get into some definitions and into some formulas. Those symbols will make more sense. You see the units there in that column, and then the abbreviations for those units, which will be very useful as we go through some of our problems. So from the basic standardized units, you get what's called derived units. And so a standard unit is obtained by mathematically combining fundamental units. And so some of those that you look at is if you look at area, well, you're going to take the standard length and you're going to square that. Force, those are measured in what we call newtons. You have electrical charges measured in coulombs, and some derived units are obtained from other derived units. And so as you move into different problems, then you are going to take the basic units and you may be talking about different dimensions that affect those units. So this moves us into everyone's favorites, which is unit conversions. And so when you look at unit conversions, you have to look at some prefixes, how you're moving from a basic unit to another unit. And most commonly ones that you're going to see, there's a whole list of them, but the ones that you're going to see the most are the kilo, the centi, and the milli. And so I'm sure you've seen them like centimeter, millimeter. That's what we're talking about when we look at those prefixes. So there's a whole list of prefixes. You don't have to memorize all your different prefixes. What you do need to understand is that they are all factors that are being multiplied by 10 to a power. And so if you take your basic unit and you apply one of these bases to it, if you were to take decimeter, centimeter, millimeter, then you can see that that all relates to your meters based on the base meter there, 10 to the 0. And then as you apply these prefixes, it affects how you're going to convert that particular factor. That is why it is called the conversion factor. This is the fraction that contains the new and the original units, and it is equivalent to 1. So for example, if you have 1 meter, that equals 100 centimeters. And so when you put 100 centimeters over 1 meter, that just equals 1 because those are the same thing. If you divide anything by itself, you get 1. And this is called dimensional analysis. This is how we convert from one unit of measure to another. So let's look at this example. It says convert 125 kilometers per hour to meters per second. And so you want to set this up with the numerator as it's given to you, 125 kilometers. And that per tells you that you are now putting it in fraction here, 125 kilometers per 1 hour. And we want to convert it to meters per second. So we're going to start with the kilometers and the meters. When you do your conversions here, you want to make sure that wherever the unit was, you're going to do it the opposite. For example, this kilometer is in the numerator. We're going to make sure that it is now in the denominator. So we're going to go from kilometers to meters. And so what we need to do is we need to say, well, how many meters are in a kilometer? That is 1,000. And so that is just multiplying by 1. 1,000 meters is the same as 1 kilometer. So we've basically divided something by itself, which means we're just multiplying by 1. We're not actually changing it if we multiply by 1. And then we need to change this hour to seconds. And so again, the hour is in the denominator. So we need to make sure that the hour is in the numerator. 1 hour is 60 seconds. And so again, 1 hour divided by 60 seconds is just one. We have not changed anything by multiplying by this. We are simply converting the units. A good way to check if you did this correctly is everything that you're getting rid of should cross cancel out, and you should be left with what you want. So I have a kilometer on the numerator. I can cross cancel it with a kilometer in the denominator. I have an hour in the denominator. I can cross cancel it with an hour in the numerator, which means I am left with meters per second, and that is what I'm looking for. And at this point, you could cross cancel if you want. You are going to be using a calculator, so you don't really have to. You can just multiply the numerator straight across. So you have 125 times 1,000 times 1. And in the denominator, you have 1 times 1 times 60. Obviously, you don't necessarily have to do that denominator in your calculator, but as you do it, your calculator work, you have to think order of operations. So you do have to put parentheses around this when you do those multiplications. And I'm showing you the ones because in case it were not a one, you would want to do it correctly. In your calculator, you want to include those parentheses. Again, you don't have to show the 1 times 1. I'm just showing to you in case you had a different number there. And then as we convert it, you should get 34.7 meters per second. So going back to our original question, how do units help us make sense? Well, units provide a standardized basis for comparison. They're useful for making measurements and discussing measurements by different scientists. We're all speaking the same language if we have a standard unit of measure.